For millennia, humanity has scanned the heavens, seeking reflections of ourselves, echoes of life. But what if the most profound answers lie not in familiar mirrors, but in realms utterly alien, sculpted by rules we're only beginning to comprehend? Imagine a world veiled in a swirling hydrogen atmosphere, a perpetual twilight above an ocean so deep and vast it dwarfs Earth's watery expanse. Here, under immense pressure and a dim, distant stellar glow, a unique chemistry might unfold, giving rise to life forms beyond our wildest terrestrial dreams. It is a vision that challenges our most fundamental assumptions about the conditions necessary for biology to take root and flourish. Then, a whisper from the cosmic distance, from a planet designated K2-18b, situated over 100 light-years away. New data arrived, and within its atmospheric signature, a revelation: the unmistakable detection of dimethyl sulfide. This isn't just another distant world added to our ever-growing catalogue of exoplanets. It's a potential paradigm shift in astrobiology. If life can thrive under such profoundly different conditions, within a hydrogen-rich atmosphere over a global ocean, then the universe, far from being a desolate void, might teem with biospheres we once deemed impossible. It broadens the canvas of potential habitability to include worlds that defy our Earth-centric expectations, forcing us to reconsider the cosmic prevalence of life itself. In this documentary, we embark on a scientific odyssey to K2-18b. Join us as Terran ventures to the fringes of current knowledge, to a world that could redefine the very definition of life in the cosmos, and perhaps our place within it. Prepare yourselves, we begin. Our cosmic narrative truly began to broaden with the advent of dedicated exoplanet hunting missions, among them the trailblazing Kepler Space Telescope. Launched by NASA in 2009, Kepler's primary objective was to survey a portion of our galaxy to discover Earth-size and smaller planets in or near the habitable zone of their stars, essentially answering the profound question of how common planets like our own truly are. Its revolutionary approach was the transit method, patiently observing the slight rhythmic dimming of a star's light as an orbiting planet passed between it and our telescopes. Each minuscule dip in brightness, a cosmic shadow play, offered a tantalizing clue to a world unseen. It was during the K2 mission, the second life of the Kepler telescope after a mechanical failure partially crippled its original pointing capabilities, that K2-18b first emerged from the silent data streams. The Kepler spacecraft, operating with renewed ingenuity, scanned different regions of the sky, meticulously recording the light curves of thousands of distant suns. In 2015, analysis of these light patterns revealed a faint, periodic flicker emanating from the red dwarf star K2-18, signalling the presence of an orbiting companion. This subtle signature, a testament to the exquisite sensitivity of our instruments, marked the formal introduction of K2-18b to humanity's scientific lexicon, placing it squarely on the map of intriguing exoplanets. Initial observations derived from the transit data allowed astronomers to begin piecing together a profile of this enigmatic world. The depth of the star's dimming during K2-18b's passage provided its approximate radius, indicating a planet roughly 2.6 times the size of Earth. Complementary follow-up observations using ground-based telescopes, employing the radial velocity method, detecting the gravitational wobble imparted by the planet on its host star, revealed K2-18b's mass to be around 8.6 times that of our homeworld. These two crucial measurements, radius and mass, allowed for a preliminary calculation of its density, a figure that immediately sparked intense scientific debate and set K2-18b apart from many of its discovered peers. This calculated density placed K2-18b firmly within a class of celestial bodies known as sub-neptunes. To understand the significance of this classification, we must first acknowledge a peculiar gap in our own solar system. We have small, rocky planets like Earth and Mars, and we have gas giants like Jupiter and Neptune. What we lack are worlds of intermediate size, planets larger than Earth but substantially smaller than Neptune. Yet, astronomical surveys have revealed that sub-Neptunes are, in fact, one of the most common types of planets across the galaxy. K2-18b, with its dimensions, is a quintessential example of this prevalent but locally absent planetary category. instantly suggesting an internal structure and atmospheric composition vastly different from either terrestrial worlds or gas giants. The very concept of a sub-neptune implies a complex layered architecture that defies simple categorization. Unlike Earth, it is too large and too low in density to be purely rocky, likely possessing a substantial envelope of volatile compounds. Yet, it is far too small and dense to be a true gas giant like Neptune, which primarily consists of hydrogen and helium with a comparatively small core. Scientists theorize that sub-Neptunes likely harbor a significant proportion of water, ice, or other heavy elements, perhaps featuring deep, supercritical fluid oceans beneath a thick gaseous atmosphere. K2, or 18b, therefore, emerge not as another potential Earth twin, but as a representative of an entirely different branch of planetary evolution, pushing our understanding of planetary formation and composition into new, uncharted territory. Central to K2-18b's potential for habitability is its host star, K2-18. This is not a Sun-like star, but an M-dwarf, often referred to as a red dwarf. M-dwarfs are the most common type of star in our galaxy, accounting for nearly 75% of the stellar population. They are considerably smaller, cooler, and less luminous than our Sun, emitting light predominantly in the infrared spectrum. Their prolonged lifespans, stretching for trillions of years, offer an immense evolutionary timescale for any life that might emerge on their orbiting planets. However, their smaller size means that for a planet to receive sufficient stellar energy to host liquid water, it must orbit much closer to its star than Earth orbits the Sun. This proximity introduces a unique set of challenges for habitability around M-dwarfs. While long-lived, these stars are often far more active and volatile in their youth, prone to unleashing powerful flares that can strip away planetary atmospheres or bathe their worlds in lethal doses of ultraviolet and X-ray radiation. Furthermore, planets in such close orbits are frequently tidally locked, a phenomenon where one side of the planet perpetually faces its star, much like our Moon always shows the same face to Earth. This creates extreme temperature gradients, with one hemisphere enduring eternal searing daylight and the other plunged into endless frigid night. The region between, the terminator zone, could potentially offer a narrow band of stable temperatures, but overall, tidal locking complicates the emergence and sustainability of widespread life. K2-18b's orbital dance around its M-dwarf parent star, K2-18, is indeed a tight one. Completing a full revolution in approximately 33 Earth days, it orbits at a distance significantly closer than Mercury orbits our Sun. This close proximity means that K2-18b is almost certainly tidally locked to its star. However, the precise atmospheric dynamics and oceanic circulation on a tidally locked world can be complex, potentially distributing heat more evenly than a simplistic day-night dichotomy might suggest. Global atmospheric currents and massive ocean flows could hypothetically mitigate the most extreme temperature differences, creating a more temperate environment across the planet, particularly if a substantial atmosphere is present. Crucially, despite its host star being an M-dwarf and its orbital period being so short, K2-18b resides squarely within K2-18's habitable zone. This Goldilocks zone is defined as the range of orbital distances where a planet can maintain liquid water on its surface, a fundamental prerequisite for life as we understand it. For a dim red dwarf like K2-18, this habitable zone is far closer to the star than for a Sun-like star. This placement suggested that, at least from a stellar energy perspective, K2-18b was receiving just the right amount of warmth to potentially sustain vast reservoirs of liquid water, setting the stage for the even more profound discoveries that would follow and propelling it to the forefront of exoplanetary research. Thus, K2-18b quickly established itself as a truly exceptional candidate in our search for life beyond Earth. It was not merely a planet in a habitable zone, but a sub-Neptune, a type of world entirely alien to our solar system's experience, orbiting a common long-lived M-dwarf star. These combined factors immediately presented a fascinating paradox, a world that was simultaneously common in the galaxy, yet utterly unique from a terrestrial perspective, offering an unparalleled opportunity to explore forms of habitability that push beyond our ingrained biases. The initial detection and characterization of K2-18b revealed a world of immense scientific intrigue, setting the stage for deeper investigations into its atmospheric composition and, ultimately, the tantalizing prospect of life. The detection of a distant exoplanet, no matter how intriguing, is merely the first chapter in its cosmic biography. To truly understand a world like K2-18b, to move beyond its size and orbital period, requires piercing the veil of its atmosphere. This endeavour, a triumph of remote sensing, is akin to deciphering a complex message encoded in starlight, allowing us to glimpse the very breath of an alien world. The primary tool for this extraordinary feat is transit spectroscopy, a method that leverages the same transit phenomenon that first revealed the planet's existence. As K2-18b periodically passes in front of its host star, a fraction of the star's light filters through the planet's tenuous atmospheric layers before reaching our telescopes. During this passage, specific molecules within the atmosphere absorb certain wavelengths of that starlight, leaving behind telltale dark lines or dips in the star's spectral signature. Each element and compound has a unique absorption fingerprint, much like a cosmic barcode. By meticulously analysing these subtle shifts and missing wavelengths, scientists can identify the chemical composition of a planet's atmosphere from light years away. This exquisite sensitivity transforms the distant glare of a star into an astronomical probe, revealing secrets once thought forever hidden. For K2-18b, the venerable Hubble Space Telescope was instrumental in performing these initial, groundbreaking atmospheric observations. Its unparalleled stability and keen vision in the visible and near-infrared spectrum allowed astronomers to collect the faint, filtered starlight during K2-18b's transits. The data collected by Hubble, painstakingly processed and analysed, began to paint the first detailed portrait of K2-18b's atmospheric makeup. This was not a simple task. The signals are incredibly subtle, requiring sophisticated algorithms and a deep understanding of atmospheric physics to disentangle from background noise and stellar interference. The initial and most significant finding from Hubble's spectroscopic analysis was the resounding confirmation of a hydrogen-rich atmosphere. This wasn't entirely unexpected for a planet of K2-18b's size and density. Sub-neptunes are theorized to retain primordial hydrogen and helium envelopes from the protoplanetary disk in which they formed, particularly if they are not too close to their star or subjected to intense stellar radiation. However, the definitive detection provided crucial empirical evidence, aligning K2-18b with models suggesting a thick extended gaseous layer, vastly different from Earth's nitrogen-oxygen dominant air. This hydrogen envelope is not merely a thin skin. It is a substantial insulating blanket, exerting immense pressure on the layers beneath. The presence of a thick hydrogen atmosphere has profound implications for K2-18b's internal conditions. Hydrogen, being the lightest element, would form a vast, puffy envelope, contributing significantly to the planet's observed radius while keeping its overall density relatively low. This gaseous blanket would also act as a potent greenhouse agent, trapping heat and potentially raising temperatures in the lower atmospheric layers and beneath. Such an atmosphere would create an environment unlike anything we experience on Earth, where the very air we breathe is a comparatively thin film. On K2-18b, the sky would be a crushing, opaque expanse of light elements, transitioning slowly and seamlessly into deeper, more exotic states. Building upon the hydrogen detection, Hubble's data also yielded another compelling signature: the presence of water vapor. This was a critical moment in the scientific understanding of K2-18b. While a hydrogen atmosphere suggested a world far from Earth-like, the clear spectral lines of water vapor provided the tantalizing hint that liquid water, the universal solvent for life as we know it, might exist beneath that thick gaseous shroud. The water vapor wasn't necessarily indicative of exposed surface oceans, but rather implied a substantial reservoir of water, likely in a liquid or supercritical state, sandwiched between the planet's rocky core and its hydrogen atmosphere. This discovery of both hydrogen and water vapor within K2-18b's atmosphere served as the primary observational evidence for a theoretical class of planets dubbed Hycean worlds. Coined by scientists, the term Hycean combines hydrogen and ocean, succinctly describing planets characterized by thick hydrogen-rich atmospheres overlying deep global water oceans. K2-18b, therefore, became the archetypal example of a Hycean planet, a concept that fundamentally redefines our understanding of habitability and expands the cosmic real estate where life might flourish. It challenged the long-held, almost exclusive focus on rocky Earth-sized planets with thin, breathable atmospheres. A Hycean world, as theorized, could maintain habitable conditions not on an exposed surface, but within its vast, pressurized subsurface ocean. The thick hydrogen atmosphere acts as a protective shield, buffering the ocean from harsh stellar radiation and moderating temperature extremes. Even though K2-18b orbits a cooler red dwarf, the greenhouse effect from its dense hydrogen layer, combined with potential internal heating from radioactive decay in its core, could maintain the deep ocean in a temperate liquid state. This scenario opens up an entirely new avenue for astrobiological exploration, suggesting that life could thrive in these hidden aquatic realms, completely isolated from the surface conditions and direct stellar light. The implications of a Hycean K2-18b are profound. It suggests that the search for life should not be confined to Earth analogues, but should embrace the diverse and often counterintuitive forms that planetary evolution can take. The sheer abundance of sub-neptunes and M-dwarf stars in our galaxy means that Hycean worlds could be far more common than traditional Earth-like planets. If life can indeed emerge and persist in these deep, hydrogen-shrouded oceans, then the universe could be teeming with biospheres, operating under vastly different energetic and environmental paradigms than our own. This conceptual leap transforms K2-18b from a mere dot in the sky into a potential beacon for a new understanding of cosmic biology. While the Hubble Space Telescope provided the initial crucial evidence, the full potential of K2-18b as a Hycean world, and indeed a potentially habitable one, would require even more powerful instruments. The very nature of transit spectroscopy, which only captures a thin slice of the atmosphere, meant that the early detections were a tantalizing glimpse, not a definitive portrait. However, the robust signals of hydrogen and water vapor were enough to elevate K2-18b to the forefront of exoplanetary research, setting the stage for future, more detailed investigations that would push the boundaries of our observational capabilities and our imagination. The classification of K2-18b as a sub-neptune is more than a mere taxonomic label. It highlights a profound paradox in our understanding of planetary architecture. Our own solar system, for all its diversity, presents us with a rather neatly divided planetary family. Small rocky worlds like Earth and Mars, and massive gas and ice giants like Jupiter and Neptune. There is no intermediate step, no world that bridges the substantial gap between Earth's familiar solid surface and Neptune's deep, icy, gaseous embrace. Yet, statistical analyses of exoplanet discoveries reveal that planets in this intermediate size range, roughly between 1.5 and 3.5 times Earth's radius, are incredibly common, perhaps the most prevalent type of planet in the galaxy. K2-18b, with its radius of approximately 2.6 Earth radii and a mass of about 8.6 Earth masses, is a quintessential example of this ubiquitous yet locally absent planetary class. This sub-Neptune paradox challenges the notion that our solar system's planetary census is representative of the galaxy at large. It compels scientists to consider new models of planetary formation and evolution that can account for the sheer abundance of these enigmatic worlds. Unlike rocky planets, sub-Neptunes are too large and possess too low a density to be composed primarily of silicates and metals. Conversely, they are too small and too dense to be true gas giants, which are predominantly made of hydrogen and helium throughout their bulk. Their existence points to a distinct evolutionary pathway, suggesting a composition dominated by lighter, more volatile materials, but in a compressed, layered configuration. The leading theoretical models for sub-Neptunes like K2-18b propose a layered internal structure, a cosmic onion of sorts, each layer dramatically different from the last. At its heart, K2-18b is believed to possess a solid, rocky core, perhaps 2 to 3 times the mass of Earth. This core would be composed of silicate minerals and iron, much like Earth's own mantle and core, albeit under far greater pressures due to the overlying layers. The intense gravitational forces would compress this material to extreme densities, potentially creating a super-Earth-like bedrock foundation for the world above. Encasing this rocky core, models suggest, is where K2-18b truly diverges from terrestrial planets. It is thought to harbour a massive liquid water layer, an ocean of truly colossal proportions. This isn't merely a surface ocean, it's envisioned as a global envelope of water, perhaps tens or even hundreds of kilometres deep, dwarfing Earth's comparatively shallow seas. The sheer volume of water could be staggering, accounting for a significant fraction of the planet's total mass. Under the immense pressures exerted by the thick atmosphere above and the gravity of the core below, this water would exist in exotic states. Near the core, it might form supercritical water, a phase where liquid and gas properties blur, or even various forms of high-pressure ice that are stable at temperatures far exceeding those that would melt ice on Earth. This deep ocean is a defining characteristic of the Hycean world hypothesis, offering a vast potential reservoir for liquid water and, consequently, life. Above this gargantuan water layer, and forming the outermost shell of the planet, lies the thick, hydrogen-rich atmosphere detected by the Hubble Space Telescope. This atmospheric envelope, a remnant from the planet's formation within the protoplanetary disk, would extend for hundreds or even thousands of kilometres into space. It's not merely air, it's a dense insulating blanket of hydrogen, helium, and trace amounts of other gases, including the water vapour that was also observed. This envelope is critical to K2-18b's internal conditions. Its mass and composition dictate the pressure and temperature profiles throughout the underlying ocean, effectively acting as a cosmic thermostat and pressure regulator for the water beneath. The atmospheric pressure at the base of this hydrogen envelope, just above the liquid ocean, would be immense, potentially hundreds or even thousands of times greater than Earth's atmospheric pressure at sea level. This extreme pressure would keep the water in its liquid or supercritical state, preventing it from boiling away into space, even if temperatures were elevated. The thick atmosphere also acts as a potent greenhouse, absorbing and re-emitting infrared radiation, thus maintaining the deep ocean at potentially warm, temperate temperatures, despite K2-18b orbiting a relatively cool red dwarf star. This delicate balance of pressure, temperature, and composition is what makes the Hycean world model so compelling for habitability. Consider the energetic implications of this internal structure. The rocky core would likely still possess a degree of internal heat from its formation, and ongoing radioactive decay similar to Earth. This geothermal energy would contribute to heating the overlying ocean from below. Combined with the atmospheric greenhouse effect, this internal heating could create a stably warm environment within the deep ocean, entirely independent of stellar illumination. This means that even if K2-18b were tidally locked, presenting one face to its star in perpetual daylight and the other in eternal night, the subsurface ocean could maintain a relatively uniform and temperate environment, shielded from the drastic temperature swings that would afflict a surface exposed to such conditions. The sheer scale of this deep ocean also plays a crucial role. A global ocean, perhaps 50 to 100 times deeper than the Mariana Trench, would offer an enormous volume for chemical reactions and potential biological processes to unfold. The interface between the rocky core and the liquid water layer would be a dynamic zone, potentially rich in hydrothermal vents, supplying chemical energy and nutrients. This scenario, reminiscent of Earth's own deep-sea hydrothermal ecosystems, suggests alternative energy sources for life that do not rely on photosynthesis, making light a less critical factor for the emergence and sustenance of a biosphere. The sub-neptune classification, therefore, does not diminish K2-18b's potential for life. It merely reshapes our perception of it. Instead of searching for another Earth, we are prompted to consider a new archetype, a world where life might thrive in a vast subterranean ocean, insulated by a thick hydrogen blanket and powered by geochemical processes. K2-18b stands as a powerful testament to the diversity of planetary forms and the ingenuity of the universe itself, urging us to broaden our scientific imagination and prepare for discoveries that may profoundly challenge our terrestrial biases. This distinct internal structure and atmospheric composition are what make K2-18b not just a planet of interest, but a potential laboratory for understanding life in radically different cosmic contexts. Having established K2-18b as a compelling Hycean world with a hydrogen-rich atmosphere and evidence of water, the stage was set for an even more profound investigation. The next chapter in this cosmic story unfolded with the deployment of the James Webb Space Telescope, an instrument of unprecedented sensitivity and infrared vision. While Hubble provided crucial initial insights, Webb's superior capabilities promised to peer deeper into K2-18b's atmospheric layers, searching for more subtle chemical signatures that could truly hint at the presence of life. Its mission was to push beyond the general composition and seek the faint, specific molecular fingerprints that could elevate K2-18b from merely habitable to potentially inhabited. In September 2023, the scientific community and indeed the world received a groundbreaking announcement. The James Webb Space Telescope had not only confirmed the presence of methane and carbon dioxide in K2-18b's atmosphere, but more astonishingly, had also detected tentative evidence of a molecule known as dimethyl sulfide, or DMS. This discovery was a seismic event in exoplanetary science, immediately catapulting K2-18b to the forefront of astrobiological inquiry. It represented a crucial step beyond merely identifying the building blocks of habitability, moving towards the actual detection of a potential biosignature. To understand the significance of dimethyl sulfide, we must first consider its role here on Earth. DMS is a simple organic sulfur compound, a gas with a distinct pungent odour, often associated with the smell of the ocean. Critically, on Earth, the vast majority, over 95% of dimethyl sulfide in the atmosphere, is produced by biological processes. It is primarily generated by marine phytoplankton, microscopic algae that float in the upper layers of the ocean. These organisms produce a precursor molecule called dimethyl sulfoniopropanate, or DMSP, which then breaks down into DMS. This compound plays a vital role in Earth's climate system, acting as a major source of sulfur aerosols that can seed cloud formation over the oceans, influencing global temperatures and precipitation patterns. Its strong correlation with marine biology makes it a compelling biosignature, a chemical compound whose presence, when observed in an exoplanet's atmosphere, suggests the existence of life. The detection of DMS in K2-18b's atmosphere, therefore, presented an extraordinary possibility that a thriving, active biosphere might exist within its conjectured subsurface ocean. The implications are profound. If the DMS observed on K2-18b has a biological origin similar to Earth's, it would suggest the presence of microbial life, perhaps analogous to phytoplankton, actively engaged in metabolic processes that produce this gas. Such a discovery would not only confirm the existence of alien life, but would do so on a world radically different from our own, further expanding the cosmic canvas for biology. However, scientific rigor demands caution and the exploration of all possibilities. While DMS is overwhelmingly biogenic on Earth, the universe is vast and capable of surprises. Scientists are meticulously exploring potential abiotic or non-biological pathways for DMS formation in K2-18b's unique environment. For instance, extreme geological processes, volcanic activity, or specific atmospheric chemical reactions involving sulfur-bearing compounds could, hypothetically, produce DMS without the need for life. The interaction of hydrogen, carbon, and sulfur in a high-pressure, high-temperature environment, perhaps near the rocky core or within hydrothermal systems in the deep ocean, cannot be definitively ruled out as a source. This is precisely where the detective story aspect of science comes into play. The James Webb Space Telescope's data provided a tentative detection, meaning the signal was observed but requires further confirmation and a more precise measurement of its abundance. Future observations with Webb, as well as potentially next-generation telescopes, will aim to refine this detection, measure the concentration of DMS more accurately, and search for other correlated molecules that could either support or refute a biological origin. For instance, the presence or absence of other sulfur-containing compounds, or the specific ratios of isotopes within the DMS molecule could provide crucial clues to its genesis. The significance of DMS as a biomarker also lies in its gaseous nature. For a gas produced by subsurface life to be detected in the upper atmosphere, there must be a mechanism for its transport. This implies a dynamic interaction between K2-18b's deep ocean and its thick hydrogen atmosphere. Volcanic outgassing, hydrothermal plumes, or even atmospheric circulation patterns could carry biologically produced gases from the ocean depths into the detectable atmospheric layers. Understanding these transport mechanisms is crucial for interpreting the observed DMS signal and for modelling the potential biosphere of K2-18b. It also suggests a world of active geological and atmospheric processes, supporting a dynamic environment conducive to life. The DMS finding, alongside the confirmed presence of methane and carbon dioxide, paints an increasingly detailed picture of K2-18b's atmospheric chemistry. Methane and carbon dioxide are common atmospheric constituents, but their abundance and ratios can offer insights into planetary processes, including potential biological activity. For example, on Earth, methane is produced both biologically and geologically. The combination of these gases, especially with DMS, provides a complex puzzle for astrobiologists to solve, using sophisticated photochemical models to simulate K2-18b's atmospheric reactions and identify which chemical pathways are most plausible. Ultimately, the detection of dimethyl sulfide on K2-18b represents a landmark moment in our quest for extraterrestrial life. It moves the discussion beyond theoretical habitability to empirical evidence, however tentative, of a potential biosignature. It signifies a profound shift from merely asking, "Are there other worlds like ours?" to "Are there other forms of life, even on worlds unlike ours, leaving their indelible chemical fingerprints across the cosmos?" This singular finding has energized the scientific community, transforming K2-18b from an interesting sub-neptune into one of the most compelling targets in the entire galaxy for the search for alien life, compelling us to consider the universe as a potentially far livelier place than previously imagined. The implications of confirming a biological origin for DMS on K2-18b would be truly revolutionary, forever altering humanity's place in the cosmic narrative. The detection of water vapor and a hydrogen-rich atmosphere on K2-18b, coupled with its sub-Neptune classification, has fundamentally reshaped our understanding of planetary habitability. For decades, the search for life beyond Earth was largely guided by an Earth-centric paradigm, focusing on rocky planets of similar size, orbiting sun-like stars within their Goldilocks zone. This approach, while logical, implicitly limited the scope of our cosmic search, assuming that life would invariably arise and thrive under conditions closely mirroring our own. K2-18b, however, has emerged as the poster child for a revolutionary concept: the Hycean world hypothesis. The term Hycean, a portmanteau of hydrogen and ocean, was coined by researchers to describe a new class of potentially habitable exoplanets. These are worlds characterized by massive hydrogen-dominated atmospheres overlying vast, deep liquid water oceans. Unlike Earth, where the atmosphere is a thin envelope of nitrogen and oxygen, and the oceans are confined to a surface, Hycean worlds propose a layered structure where a thick gaseous blanket insulates a global ocean that might stretch for hundreds of kilometers deep. K2-18b, with its confirmed atmospheric composition and inferred internal structure, fits this definition precisely, making it a critical test case for this novel concept. The Hycean world hypothesis profoundly challenges the traditional Earth-centric view of the habitable zone. Previously, models largely focused on planets that could maintain liquid water on their surface. For an M-dwarf star like K2-18, this habitable zone is typically much closer than for a Sun-like star, raising concerns about tidal locking and intense stellar flares. However, for a Hycean world, the thick hydrogen atmosphere acts as an extraordinary buffer. This dense atmospheric envelope can effectively shield the underlying ocean from the harsh radiation and energetic particles emitted by its host star. Furthermore, the substantial greenhouse effect generated by such a thick atmosphere can warm the deep ocean to temperatures conducive to liquid water, even if the stellar insulation at the top of the atmosphere is relatively low. This means a Hycean planet could maintain internal ocean habitability across a much broader range of orbital distances, effectively expanding the habitable zone for this specific type of world. The implications for the prevalence of life in the universe are staggering. Sub-Neptunes, the size class K2-18b belongs to, are estimated to be the most common type of exoplanet in the Milky Way. M-dwarf stars, K2-18's stellar type, are also the most abundant stars in our galaxy. If a significant fraction of these common planetary and stellar types can host Hycean conditions suitable for life, then the total number of potentially inhabited worlds in the cosmos could be exponentially higher than previously thought. This vastly expands the search space for extraterrestrial biology, moving beyond the rare Earth 2.0 analogues to embrace a far more diverse spectrum of potentially life-bearing environments. Consider the thermal dynamics of such a world. While K2-18b is tidally locked to its star, meaning one side perpetually faces its sun and the other is in eternal darkness, the thick hydrogen atmosphere could effectively redistribute heat across the planet. Powerful atmospheric currents, driven by the intense temperature contrast between the day and night sides, would circulate vast quantities of heat, preventing the day side from scorching and the night side from freezing. More importantly, the immense volume of the subsurface ocean itself would act as a massive heat sink and reservoir, maintaining a remarkably stable temperature throughout its depths, largely decoupled from the surface atmospheric extremes. This internal stability is crucial for sustained biological evolution, offering a long-term, buffered environment for life to develop. Moreover, the sheer depth and volume of a Hycean ocean present unique advantages for life. Such an ocean could provide a stable environment for billions of years, protected from surface impacts, solar flares, and atmospheric stripping. The pressure at great depths would be immense, but life on Earth has shown remarkable adaptability to extreme conditions, including the crushing pressures of our own abyssal trenches. The interface between the water and the rocky core could host hydrothermal vents, providing chemical energy and mineral nutrients, similar to Earth's chemosynthetic ecosystems. These vents, driven by geological activity, could fuel entire food webs independent of stellar light, offering a robust foundation for an alien biosphere. The Hycean hypothesis also forces us to reconsider the definition of life as we know it. While the presence of liquid water remains a universal prerequisite, the chemical environment within a hydrogen-rich atmosphere and deep ocean could be dramatically different from Earth's. Hydrogen is a powerful reducing agent, meaning it readily donates electrons. This could favour different metabolic pathways than those prevalent on Earth, which often involve oxygen as an electron acceptor. Life on K2-18b might utilise hydrogen directly as an energy source or in novel biochemical reactions, operating within a metabolic framework we are only beginning to conceptualise. This prospect moves beyond simply finding pond scum to envisioning entirely new biochemistries. The discovery of K2-18b and the subsequent development of the Hycean world concept represent a pivotal moment in astrobiology. It is a testament to the power of observational astronomy and theoretical modelling to push the boundaries of our imagination. By identifying and characterising worlds like K2-18b, we are not just adding names to a list. We are fundamentally rewriting the textbook on planetary habitability. We are moving towards a more inclusive and expansive view of where life can exist, suggesting that the universe might be far more hospitable and biologically rich than our limited terrestrial perspective once allowed us to believe. K2-18b stands as a vibrant beacon, illuminating a new pathway in our quest to answer the most profound question: are we alone? And the Hycean world hypothesis offers a compelling argument that the answer might very well be no, and that life, in its myriad forms, could be far more common than previously dared to imagine. With K2-18b firmly established as a prime candidate for a Hycean world, the scientific inquiry shifts from detecting its atmospheric components to imagining the environment within its vast hidden ocean. This deep dive into theoretical planetary interiors allows us to speculate on the conditions that might prevail beneath a crushing hydrogen atmosphere, revealing a realm of immense pressure, unique thermal dynamics, and exotic chemistry. It's a journey into the unseen, a reconstruction based on physics, chemistry, and the tantalizing clues gathered from afar. The very first condition to grasp about K2-18b's conjectured subsurface ocean is the immense pressure. The detected hydrogen-rich atmosphere is not a thin veil. It's a colossal blanket of gas, extending for hundreds, if not thousands, of kilometres. This gaseous envelope exerts a crushing force on the layers beneath. At the interface between the atmosphere and the liquid ocean, the pressure would already be orders of magnitude greater than Earth's sea level pressure, potentially hundreds or even thousands of bars. As one descends deeper into the ocean, this pressure would only intensify, reaching unimaginable levels closer to the rocky core. This extreme pressure fundamentally alters the properties of water, forcing it into states rarely, if ever, seen on Earth, except in specialized laboratories. Under such pressures, water behaves dramatically differently. While it remains liquid, its density would increase significantly. Moreover, at certain depths and temperatures, exotic forms of high-pressure ice, structurally distinct from the ice we know, could form. These ices are stable at temperatures far above water's normal freezing point, acting more like solid rock than frozen water. This means the ocean might not be uniformly liquid throughout its entire depth. Instead, it could be layered, with regions of liquid water transitioning into superionic ice or other high-pressure phases closer to the rocky core. Such phases could influence nutrient transport, energy distribution, and the very viability of life. The temperature profile within K2-18b's deep ocean is another critical factor. Despite orbiting a relatively cool M-dwarf star, the thick hydrogen atmosphere acts as a powerful greenhouse. Hydrogen is an excellent absorber of infrared radiation, effectively trapping heat within the planet's envelope. This means that the base of the atmosphere and the upper layers of the ocean could be surprisingly warm. Furthermore, internal heating from the planet's rocky core, generated by residual heat from its formation, and the ongoing radioactive decay of elements like uranium, thorium, and potassium, would contribute significantly to the overall thermal budget. This internal geothermal energy would warm the ocean from below, potentially creating a stable, temperate environment throughout much of its vast volume. This combination of atmospheric greenhouse effect and internal heating suggests that K2-18b's ocean could be maintained at temperatures conducive to liquid water, perhaps even reaching ranges considered temperate for terrestrial life. However, it's not a simple uniform warmth. There would likely be a thermal gradient, with temperatures potentially increasing closer to the rocky core due to geothermal activity. This gradient could drive convection currents within the ocean, circulating heat and nutrients, and creating dynamic environments for potential biological activity. The sheer volume of water also provides immense thermal inertia, meaning temperatures would be incredibly stable over vast timescales, an essential condition for the long-term evolution of life. Beyond pressure and temperature, the chemistry of K2-18b's ocean would be profoundly shaped by its hydrogen-rich environment. In chemical reactions, this stands in stark contrast to Earth's oxygen-rich atmosphere and oceans, which are oxidizing environments. Life as we know it on Earth is largely based on redox reactions involving oxygen, but in a hydrogen-dominated system, different metabolic pathways and biochemical processes might be favored. Organisms could potentially phase, forming the basis of an entirely different kind of biochemistry. The interaction between the deep water and the rocky core is also a critical zone for exotic chemistry. Hot, pressurized water could react with the silicate rocks and metals of the core, leading to serpentinization and other geochemical processes. These reactions would release dissolved minerals and energy-rich chemical compounds, such as methane, hydrogen, and various sulfur compounds, into the ocean. These hydrothermal vent systems, analogous to those found in Earth's deep oceans, could provide the necessary ingredients and energy gradients for chemosynthetic life to emerge and thrive, completely independent of light from the distant star. The detection of dimethyl sulfide, a sulfur compound, further underscores the potential for complex sulfur chemistry within this system. Furthermore, the absence of a direct surface interaction with the star for the bulk of the ocean means that conventional photosynthesis, reliant on stellar photons, might be impossible for deep-dwelling life. Instead, chemosynthesis, harnessing chemical energy from geological processes, would likely be the dominant primary productivity mechanism. This shifts the energy paradigm entirely, focusing on subterranean processes rather than surface-level solar energy. The ocean, therefore, becomes a self-contained ecosystem, potentially thriving on internal energy sources robustly buffered from the more volatile conditions above. The overall picture that emerges for K2-18b's subsurface ocean is one of a vast, dynamic, and chemically active environment. It is a world of incredible pressures, potentially temperate depths, and exotic geochemical interactions. This isn't a simple, shallow pool. It's a colossal, three-dimensional habitat, a massive reactor for complex chemistry and potentially biology. The conditions within this alien ocean push the boundaries of our terrestrial experience, forcing us to consider how life might adapt and evolve in a realm profoundly different from our own. It is precisely these extreme, yet potentially stable, conditions that make K2-18b such a compelling target for astrobiological speculation and future scientific investigation, opening our minds to the vast possibilities of the cosmos. If K2-18b does indeed harbour life within its deep hydrogen-shrouded ocean, then its evolutionary trajectory would be profoundly shaped by the planet's extreme environment. The fundamental principles of biology, metabolism, reproduction, and natural selection would undoubtedly apply, but the specific adaptations for survival in a high-pressure, hydrogen-rich and potentially low-light world would be unlike anything found in Earth's familiar biomes. We are forced to consider how life could acquire energy, cycle nutrients, and propagate itself under conditions that fundamentally challenge our terrestrial preconceptions. The most critical adaptation for any potential life on K2-18b would revolve around energy acquisition. On Earth, the vast majority of ecosystems are ultimately powered by sunlight through photosynthesis. However, within K2-18b's deep global ocean, shielded by hundreds of kilometers of water and a thick hydrogen atmosphere, stellar light would be either greatly attenuated or entirely absent. This necessitates an entirely different foundation for the food web: chemosynthesis. Life would likely derive its energy from chemical reactions, harnessing the abundant geological and geochemical processes at ocean. Imagine hydrothermal vents, similar to Earth's black smokers, permeating K2-18b's seafloor. These vents would spew superheated, mineral-rich fluids laden with reduced chemical compounds like hydrogen sulfide, methane, and molecular hydrogen. Microorganisms, the foundational life forms, would evolve to metabolize these compounds, oxidizing them to extract energy. For example, hydrogenotrophic bacteria, common on Earth, thrive by combining molecular hydrogen with carbon dioxide to produce methane and water. Such metabolisms would be ideally suited to K2-18b's hydrogen-rich environment, establishing a primary productivity entirely independent of stellar photons. This would create robust ecosystems flourishing in perpetual darkness, powered by the planet's internal heat and chemistry. The pervasive, high-pressure environment would exert immense selective pressure on the morphology and physiology of any larger multicellular organisms. Skeletons, as we know them, might be costly or even counterproductive. Earth's deep-sea creatures often possess flexible, gelatinous bodies, composed largely of water, allowing them to withstand crushing pressures without imploding. K2-18b's inhabitants might similarly evolve soft-bodied forms, perhaps resembling enormous jellyfish or other buoyant, amorphous creatures that drift through the water column, conserving energy in an environment where movement against dense fluid is challenging. Their bodies might be designed for efficient pressure equalization, perhaps through specialized membranes or internal fluid systems. Gas exchange would also present a significant evolutionary hurdle. Terrestrial life breathes oxygen, but K2-18b's ocean would be hydrogen-saturated. Organisms might evolve to utilize dissolved hydrogen directly in their metabolic processes, or perhaps other electron acceptors like sulfates or nitrates if present. Specialized biological membranes or gills designed to efficiently extract these dissolved gases from the pressurized water would be crucial. The production of dimethyl sulfide, if biological, suggests a sophisticated sulfur cycle within this alien biosphere, implying organisms capable of processing sulfur compounds as part of their metabolic repertoire. Reproductive strategies would also adapt to the vastness and darkness of the deep ocean. Dispersal of gametes or larvae in a world without significant currents or visual cues could be a challenge. Organisms might evolve strategies like bioluminescent signaling for mate attraction, or release large numbers of resilient spores that can drift for vast distances before finding suitable conditions. Some could adopt internal fertilization or even budding, ensuring that offspring develop in a protected environment. The long evolutionary timescales afforded by M-dwarf stars would allow for the development of highly specialized and efficient reproductive mechanisms. Beyond individual organisms, the structure of entire ecosystems would be profoundly affected. Without light, there would be no direct equivalent of terrestrial plants or surface-dwelling phytoplankton forming the base of the food chain. Instead, chemosynthetic microbes would form microbial mats or biofilms around hydrothermal vents, serving as the primary producers. Larger organisms would then feed on these microbes, or on each other, forming a complex web of scavengers, grazers, and predators. These deep-sea ecosystems would likely be characterized by slow growth rates, long lifespans, and energy-efficient metabolisms, reflecting the resource-limited nature of their environment. The thick hydrogen atmosphere itself could also influence life, even if indirectly. While the primary habitat is the ocean, interactions at the ocean-atmosphere interface could lead to unique evolutionary pressures. For example, if some forms of life produced gases that could escape the ocean and enter the atmosphere, like DMS, this could lead to a feedback loop where atmospheric composition is subtly influenced by biology. Organisms might also develop specialized buoyancy mechanisms, utilizing gases produced metabolically to float or migrate through different ocean layers, accessing various nutrient niches. The concept of life under these hydrogen skies forces us to move beyond our carbon-centric and oxygen-breathing biases. It challenges us to consider life that might breathe hydrogen, eat sulfur compounds, and navigate a world of crushing pressures and eternal twilight. This hypothetical biology is a testament to the versatility of life itself, a recognition that the chemical rules of the universe, combined with billions of years of natural selection, can produce solutions to environmental challenges that are as diverse as the worlds they inhabit. K2-18b offers a tantalizing glimpse into a universe where life is not a singular fragile exception, but a robust and adaptable phenomenon capable of finding a foothold in the most unexpected and seemingly extreme corners of the cosmos. This consideration is not mere fantasy. It is rigorous scientific speculation, built upon the known laws of physics and chemistry, and fueled by the data gathered from distant worlds. Having explored the environmental pressures and potential metabolic adaptations, we now embark on a deeper imaginative journey to simulate what alien ecologies might actually look like within K2-18b's colossal, subsurface ocean. This is not about conjuring fantastical beasts for entertainment, but about applying the principles of biology, physics, and chemistry to reconstruct plausible forms and interactions, painting a scientific portrait of the unseen. At the base of any K2-18b food web would be the primary producers, the microorganisms. Picture vast, shimmering microbial mats clinging to the rocky seafloor, especially in areas warmed and chemically enriched by hydrothermal vents. These mats would consist of extremophilic bacteria and archaea, analogous to Earth's chemosynthetic communities. Instead of chlorophyll, they might possess novel pigments or cellular machinery optimized to capture chemical energy from the abundant hydrogen, methane, or sulfur compounds dissolved in the ocean. These organisms could form vibrant, multi-layered communities, each layer specialized in metabolizing a different chemical gradient, creating a tapestry of alien life that coats the planet's deep, dark core. Above these microbial foundations, suspended in the immense water column, we might envision larger, soft-bodied organisms. The crushing pressures would favor streamlined, often gelatinous forms that minimize internal structural strain. Imagine creatures resembling colossal ethereal jellyfish, their bodies mostly water, perhaps with elaborate ribbon-like appendages for filter feeding on microscopic organisms or detritus. These hydrozoan leviathans could drift slowly through the ocean, their internal chemistries finely tuned to the high-pressure environment, their buoyancy regulated by specialized gas bladders filled with metabolic byproducts or by carefully controlled ion concentrations in their tissues. Their movements would be deliberate, energy-efficient, dictated by the dense fluid around them. In a world largely devoid of stellar light, bioluminescence would be a predominant form of communication, hunting, and defense. Imagine the deep ocean of K2-18b as a canvas of living light, with flashes, pulses, and intricate patterns illuminating the perpetual twilight. Predators might use luminous lures to attract prey, while prey could emit dazzling bursts of light to startle or disorient attackers. Mating rituals could involve complex bioluminescent displays, signaling species identity and reproductive readiness across vast distances. The chemical pathways for bioluminescence, like those found in Earth's deep-sea organisms, might be highly refined and diverse, producing a spectrum of alien glows. For creatures that venture closer to the hypothetical surface of the ocean, beneath the thick hydrogen atmosphere, a different set of adaptations might emerge. While direct stellar light would be heavily filtered, some faint diffuse red or infrared light from the M-dwarf star might penetrate the uppermost layers of the ocean. Here, organisms could develop rudimentary light-sensing organs, or even novel forms of photosynthesis that harness these specific low-energy photons. However, it's more probable that chemosynthesis would remain dominant, with light acting as a secondary cue or a signal rather than a primary energy source. The concept of a global deep ocean also implies vast interconnected ecosystems. Convection currents, driven by geothermal heat and atmospheric interactions, would circulate nutrients and even disperse life forms across immense distances. This could lead to a relatively uniform distribution of basic life forms, but also specialized ecosystems clustered around unique geological features or chemical anomalies. Over geological timescales, this widespread connectivity could facilitate the evolution of complex, multicellular life capable of colonizing various oceanic niches. Consider the potential for sophisticated sensory systems in such an environment. Without light, senses like echolocation, akin to bats and dolphins, or electroreception, like sharks, would be highly advantageous. Organisms might navigate and hunt by emitting sound waves and interpreting their echoes, or by detecting the subtle electrical fields generated by other creatures. Chemoreception, the sense of smell or taste, would also be paramount, allowing organisms to track chemical trails of prey or find mates in the vast darkness. These sensory adaptations would create a richly textured, if non-visual, perception of their world. The evolution of complex life might also lead to unique forms of resource partitioning. Just as on Earth, different species would occupy different trophic levels and ecological niches. There might be bottom-dwelling detritivores, filtering scavengers, and active predators. The absence of land masses within the ocean would remove a significant evolutionary driver for terrestrial adaptations, favouring exclusively aquatic forms. However, the sheer depth could create vertical stratification, with different communities thriving at different pressure and temperature regimes, forming distinct ecological zones from the relatively warmer upper ocean layers to the crushing depths near the core. Finally, the possibility of intelligent life on K2-18b, while highly speculative, compels a fascinating thought experiment. If life were to achieve consciousness in such an environment, its perception of reality would be radically different from our own. Without light, their world would be defined by sound, pressure, temperature, and chemical gradients. Their technology, if it developed, would likely be focused on manipulating these elements, perhaps for communication across vast oceanic distances, or for harnessing the planet's internal geothermal energy. Their understanding of the cosmos, derived from a deep shielded ocean, would be profoundly unique, challenging our anthropocentric views of intelligence and civilization. In simulating these alien ecologies, we are not just illustrating scientific data, we are expanding the very canvas of possibility for life in the universe. K2-18b offers a tangible, data-driven window into a world where life could flourish under parameters previously considered too extreme. It forces us to acknowledge the sheer ingenuity of natural selection and the boundless potential for evolution, suggesting that the universe might be filled with biospheres far stranger, yet no less vibrant than our own. This journey into K2-18b's hypothetical ocean is a powerful reminder that life is not merely a terrestrial phenomenon, but a cosmic one, capable of adapting to almost any niche the universe can create. The extraordinary claims surrounding K2-18b, particularly the tantalizing prospect of a biological origin for dimethyl sulfide, demand an equally rigorous and cautious scientific approach. While the data from the James Webb Space Telescope is groundbreaking, it represents a significant frontier in observation and interpretation. This is where the scientific process truly shines, acknowledging the thrilling possibilities while simultaneously confronting the challenges, limitations, and ongoing debates that are inherent to pushing the boundaries of knowledge. The journey to confirm or refute life on K2-18b is a marathon, not a sprint, fraught with both promise and uncertainty. One of the primary challenges lies in the very nature of remote atmospheric spectroscopy. We are observing the faint signatures of molecules from hundreds of light-years away, through the noise of interstellar space and the complexities of the planet's own star. The initial detection of DMS was termed tentative, because while the spectral signature was present, its statistical significance needed to be improved. This means the signal was not as strong or clear as definitive detections of more abundant molecules like water or methane. Scientists must account for every possible source of error, from instrumental noise to stellar activity that could mimic or obscure planetary signals. The immediate scientific imperative is to obtain more data. Future observations with the James Webb Space Telescope, leveraging longer integration times and potentially new observing modes, will be crucial to confirm the DMS detection with higher confidence and to precisely measure its abundance. A stronger, more unambiguous signal would significantly bolster the case for its presence. Furthermore, astronomers are eager to search for other potential biosignatures or co-occurring molecules that could either support or contradict a biological origin. For example, the absence of certain abiotic sulfur compounds that should be present if DMS were formed geologically would lend weight to the biological hypothesis. Another critical area of ongoing research revolves around the complex atmospheric chemistry of K2-18b. Even with robust detections, identifying the source of a molecule is notoriously difficult. Scientists are developing sophisticated photochemical models to simulate the atmospheric conditions on K2-18b, exploring all plausible pathways for the formation and destruction of DMS. These models take into account factors like the planet's intense stellar radiation, the high concentration of hydrogen, potential atmospheric circulation patterns, and the chemical interactions between different gases. Could a unique, high-pressure, hydrogen-rich environment create abiotic pathways for DMS production that are entirely unknown on Earth? This is a central question that needs to be thoroughly investigated before any definitive conclusions about life can be drawn. The internal structure and dynamics of K2-18b also present significant uncertainties. While the Hycean world model is compelling, it is still largely theoretical. We lack direct observational evidence of the deep ocean or the rocky core. The exact depth, temperature, and chemical composition of the ocean remain unknown, as do the extent of geological activity and the presence of hydrothermal vents. All these factors would profoundly influence the viability of life and the types of biosignatures it might produce. Refining our understanding of K2-18b's interior through improved planetary modelling, perhaps guided by future data on its precise mass and radius, is therefore essential. There is also a lively debate within the scientific community regarding the interpretation of the existing data. Some researchers are more optimistic about the biological implications of DMS, given its strong biogenic link on Earth. Others advocate for extreme caution, emphasizing the need to exhaust all abiotic explanations first. This healthy skepticism is a cornerstone of the scientific method, ensuring that extraordinary claims are met with extraordinary evidence. This ongoing dialogue, often playing out in peer-reviewed journals and scientific conferences, is a vital part of the process, ensuring that all avenues of inquiry are rigorously pursued. The very concept of a Hycean world, while exciting, also comes with its own set of theoretical uncertainties. What are the long-term stability mechanisms for such a thick hydrogen atmosphere? How does the interaction between the atmosphere, the ocean, and the rocky core evolve over billions of years? Could a planet like K2-18b transition from a potentially habitable state to an uninhabitable one, perhaps through atmospheric escape or runaway greenhouse effects, over geological timescales? Understanding these evolutionary pathways is crucial for assessing the long-term habitability of Hycean worlds in general. Looking ahead, the next generation of telescopes and instruments promises to revolutionize our ability to characterize exoplanet atmospheres. Missions currently in development, or even more ambitious concepts for the distant future, could offer even greater sensitivity, spectral resolution, and observational capabilities. These might allow for the detection of a wider suite of biosignatures, or even more definitive measurements of existing ones. The ultimate goal is to move beyond tantalizing hints to undeniable proof, a challenge that will require decades of dedicated research and technological innovation. K2-18b, therefore, stands not just as an object of study, but as a crucible for new scientific methodologies and philosophical inquiries. It forces us to confront the limitations of our current technology and understanding, while simultaneously inspiring new approaches and pushing the boundaries of what we thought was possible. The scientific frontier it represents is vast, complex, and exhilarating, reminding us that the universe holds mysteries far deeper than we can currently fathom. and that every new discovery opens up a cascade of even more profound questions. The ongoing investigation of K2-18b is a testament to humanity's relentless drive to explore, understand, and ultimately, to find our place within the cosmic narrative. K2-18b is more than a celestial body. It has become a lighthouse in the cosmic ocean, illuminating new pathways in our quest for understanding life beyond Earth. Its journey from a faint stellar flicker to a prime candidate for a Hycean world, potentially brimming with alien biology, symbolizes the incredible progress of exoplanetary science and the ever-expanding canvas of cosmic possibilities. This distant world, a sub-neptune orbiting a red dwarf, stands as a testament to humanity's evolving understanding of planetary systems and the diverse forms habitability can take. This planet has fundamentally reshaped our astrobiological perspectives. For generations, the search for life was implicitly bound by the blueprint of Earth, a rocky world, temperate, with a thin nitrogen-oxygen atmosphere, orbiting a sun-like star. K2-18b shatters this limited view. It forces us to acknowledge that the universe is far more creative than our terrestrial imagination, capable of nurturing life in environments we once considered too extreme or too alien. The Hycean world hypothesis, of which K2-18b is now the most compelling example, suggests that vast hydrogen-shrouded ocean planets could be common, dramatically increasing the estimated number of potentially life-bearing worlds in our galaxy. The significance of K2-18b lies not just in the potential detection of dimethyl sulfide, but in its role as a catalyst for scientific thought. It has motivated the development of new theoretical models, pushing planetary scientists to consider novel internal structures and atmospheric chemistries. It has spurred engineers to design even more sensitive instruments, capable of probing the faint signals from distant atmospheres with unprecedented precision. Every debate, every new paper, every planned observation of K2-18b contributes to a broader scientific framework that will ultimately benefit the entire field of astrobiology, regardless of K2-18b's ultimate biological fate. This world is a powerful symbol of our scientific ambition. It represents the culmination of decades of technological advancement, from the initial planet-hunting capabilities of the Kepler telescope to the exquisite spectroscopic power of the James Webb Space Telescope. Each successive observation, each refined analysis, builds upon the last, demonstrating the iterative and cumulative nature of scientific discovery. K2-18b is a beacon of what is possible when human curiosity is combined with ingenuity and a relentless pursuit of knowledge. It embodies the very spirit of exploration, pushing us to ask bigger questions and seek bolder answers. Furthermore, K2-18b encourages a profound philosophical shift. If life can indeed thrive in a deep, dark ocean under a thick hydrogen blanket, then the concept of alien becomes less about fantastical creatures and more about the fundamental adaptability of biology itself. It suggests that life is not a fragile anomaly unique to Earth, but a robust and resilient phenomenon, capable of finding a foothold in almost any niche where energy gradients and liquid solvents exist. This realization has the potential to profoundly impact our perception of humanity's place in the cosmos, moving us from a sense of lonely uniqueness to a more integrated view of life as a widespread, universal phenomenon, vivid demonstration of the scientific process in action. It showcases the excitement of discovery, the meticulousness of verification, the healthy skepticism of peer review, and the continuous refinement of hypotheses. The tentative nature of the DMS detection and the subsequent efforts to confirm it and rule out abiotic explanations is a perfect illustration of how science progresses, not with immediate definitive pronouncements, but through careful incremental steps, building evidence brick by painstaking brick. This transparency and rigorous self-correction are what give scientific findings their ultimate power and credibility. K2-18b is also a reminder of the vastness of the unknown. For every question it answers, it raises a dozen more. What other types of habitable worlds exist? What forms might life take under even stranger conditions? How common are planets with deep oceans, or those with hydrogen atmospheres? Each step closer to understanding K2-18b is a step further into the cosmic mystery, deepening our appreciation for the complexity and diversity of the universe. It serves as an ongoing invitation to curiosity, a perpetual challenge to our intellectual boundaries. In the grand tapestry of the cosmos, K2-18b is a vibrant thread, weaving together the disciplines of astrophysics, planetary science, chemistry, and astrobiology. It is a world that has captured the collective imagination of scientists and the public alike, inspiring a new generation to look skyward and ponder the profound question of life's origins and distribution. This sub-Neptune, with its tantalizing atmospheric secrets and the promise of a hidden ocean, is not just a scientific object. It is a symbol of hope, possibility, and the enduring human quest to understand our place in the boundless, silent expanse of the universe. Its story is far from over, and its future revelations promise to continue to redefine our cosmic perspective. Our expedition to K2-18b has traversed unimaginable distances, not just across the light years separating us from this alien world, but across the vast landscapes of scientific understanding and philosophical inquiry. From its initial detection as a faint shadow against a distant star, K2-18b has evolved from a mere data point into a vibrant, if still largely theoretical, vision of a Hycean world, a planet cloaked in hydrogen, harbouring a colossal unseen ocean, potentially teeming with life adapted to conditions once thought utterly inimical to biology. This intellectual journey compels us to reflect on the very nature of existence and humanity's place within a cosmos far stranger and more inventive than our ancestors could ever have conceived. The journey began with a planetary archetype absent from our own solar system, yet paradoxically common throughout the galaxy. This alone shattered our Earth-centric biases, forcing us to acknowledge the sheer diversity of planetary architectures. It was the first profound challenge to our assumption that life must arise on worlds mirroring our own. The subsequent detection of a hydrogen-rich atmosphere and abundant water vapour by the Hubble Space Telescope solidified its status as a potential Hycean world, a novel category of habitability where the planet's thick gaseous shroud acts as both a shield and a greenhouse, insulating a deep global ocean from the harshness of space and the vagaries of its M-dwarf star. This realization expanded the cosmic real estate for life by an order of magnitude, inviting us to look beyond the narrow confines of what we once considered a habitable zone. Then came the seismic revelation from the James Webb Space Telescope, the tentative detection of dimethyl sulfide. This molecule, overwhelmingly biogenic on Earth, became a tantalizing whisper from the depths of K2-18b, suggesting that the ocean beneath its hydrogen veil might not be silent and barren but alive. This finding ignited a new frontier in astrobiology, shifting the discourse from merely identifying the potential for life to actively searching for its fingerprints. It amplified the stakes of our cosmic quest, transforming K2-18b from a scientific curiosity into a potential laboratory for alien biology, a beacon demanding our focused attention and rigorous investigation. The subsequent intellectual leap to simulate what life might look like in such an environment pushes the very boundaries of our biological imagination. We envisioned organisms adapted to crushing pressures, thriving in perpetual twilight, powered not by stellar light but by chemosynthesis, metabolizing the very chemistry of their world, from microbial mats clinging to hydrothermal vents to gelatinous leviathans drifting through a lightless ocean. The hypothetical ecosystems of K2-18b paint a picture of life's profound adaptability. It underscores that the universe's evolutionary canvas is vast, capable of producing solutions to environmental challenges that transcend our terrestrial experience, reminding us that carbon-based life, while familiar, is but one of countless possibilities. This is where scientific rigor meets poetic grandeur, where data gives rise to daring, informed speculation. Yet, as with all truly groundbreaking discoveries, the path forward is paved with both immense excitement and necessary caution. The tentative nature of the DMS detection, the ongoing exploration of abiotic formation pathways, and the inherent limitations of remote sensing serve as critical reminders of the scientific method's demands. We stand at the precipice of a potentially revolutionary discovery, but prudence dictates that extraordinary claims require extraordinary evidence. The scientific community's diligent pursuit of confirmation, the development of ever more sophisticated models, and the planning of future observations are not impediments to progress, but rather the very engine that drives it, ensuring that any pronouncement of alien life is built on an unshakable foundation of empirical data. The enduring legacy of K2-18b, regardless of whether its DMS signature is definitively confirmed as biological, will be its profound impact on our cosmic perspective. It has forced us to confront the inherent anthropocentrism in our search for life, challenging us to expand our definitions of habitability and life itself. We are learning that the universe is not designed exclusively for Earth-like worlds, but rather exhibits a boundless creativity in crafting environments where biology might take hold. This realization imbues the cosmos with a deeper sense of wonder, transforming it from a mostly barren expanse into a potentially vibrant living tapestry woven with myriad forms of existence. This journey to K2-18b is ultimately a journey inward, a reflection on our own place within this magnificent and mysterious universe. It teaches us humility, reminding us that our planet, while precious, is but one of countless worlds. It inspires us, showing the immense power of human ingenuity to unravel cosmic secrets from light years away. And it leaves us with an even more profound question than the one we began with. If life can be so fundamentally diverse, so robust and adaptable as to thrive under a hydrogen sky and a crushing ocean, what other wonders await our discovery? What other forms of existence, beyond our wildest dreams, are currently unfolding on untold billions of worlds, waiting for us to develop the instruments, the models, and the imagination to perceive them? K2-18b is not the end of our search. It is merely the beginning of a grander, more inclusive quest for life in a universe far more astonishing than we ever dared to imagine.